origin and how these items arrived for our perusal. So thank you very much again for coming, and enjoy. Thank you.
So, I don't know if any of you have been to the new Academy in Golden Gate Park. It's very different from the old Academy. At this time, unfortunately, a lot of our collections are not on display, but we're hoping to change that as time goes on. There aren't very many places around to see meteorites. Most mineral displays have a few of them. The nearest big mineral displays are in the town of Mariposa, over near Yosemite. That's where they display the old California State collection that used to be in the Ferry Building in San Francisco. And there are some meteorites in there. I haven't looked at the list. It's currently run by state parks.
Oh.
Yeah, so I have no idea whether it's on that list of 72 parks that they're going to close. We're hoping not. And then the next nearest one is at LA County Museum and Exposition Park in Los Angeles, which is a beautiful place if you've never been there. Dinosaurs, minerals, gold, all sorts of cool stuff. And plus the Tar Pit Museum on Wilshire Boulevard is part of that, the Natural History Museum of LA County. And that's right next to the tar pit, which is still sitting there gurgling and spitting things up every once in a while. So I'm getting off the subject. At the Academy of Sciences, my job, a collections manager, is basically like a librarian. So it's very appropriate that we're here in the library. I do everything that a librarian does. I take care of the collection. I make sure it's orderly and well cared for, and I keep track of all the paperwork that goes with it, and I make it accessible to people who want to use it. So, except that instead of books, my library is rocks. So, one of the specialty collections that we have at the Academy are the meteorites. Now, meteorites are very, very special rocks. In order to be called a meteorite, they have to be on Earth. If they are pieces of material that are randomly wandering around the solar system, they are called meteoroids. And meteoroids come in all different sizes and compositions. Many of them are fragments of planets or comets or moons. Many times bits of larger bodies will be flung into space by impacts of other bodies. So if something hits Mars or Mercury, bits of that planet will fly out into space and become meteoroids. And if one of these gets caught in the gravitational field of the Earth, they enter our atmosphere and head for the ground. While they're in the atmosphere, they are called meteors because they're moving toward the Earth. And most meteors, if they have enough mass, will develop a glow like that picture. That's a real meteor. And they're glowing because they're hot. And they become hot because of the friction of the air. Remember that air is actually particles. So they're moving very fast, and they're being attacked by all those particles of air. Most meteoroids that enter the Earth's atmosphere burn up in the atmosphere. They never reach the Earth. Thousands and thousands of them hit the atmosphere every day.
Well,
But most of them never make it down to the ground. In order for that to happen, they have to be fairly sizable. So once one of these things hits the ground, it is technically a meteorite. And I realize I misspelled meteorite there on the right. I'm very sorry. When a meteor hits the ground, depending on how strong it is and what angle it's going, because some of them come in at a sideways angle and some come straight down, sometimes they break apart and they shatter into thousands of pieces. Or sometimes, if they're very strong, and the situation is right, they don't shatter and it stays in one intact mass. So there are lots of both of these types of meteors on Earth. Each meteorite is a unique individual, just like a person. And there are chemical and physical characteristics that can be used to identify them once you have characterized each one. Now, meteorites are divided into three basic groups: irons, stony irons, and stonies. Iron meteorites are the ones that everybody knows about. You know that if, you know, everybody thinks meteorites are very heavy, very dense, and they attract a magnet. Well, not all meteorites do that, but the iron ones do, because most irons are about 90% iron. And then the second most common element is nickel, and then some of them have a little bit of other things, but it's mostly iron and nickel. Now, if you look at that meteorite on the right, you can see that it looks like it was partially melted, as it was. When traveling through the atmosphere, the surface of it melted as it was moving, and it kept that sort of shiny, soft look to it when it landed. There are three kinds of irons. Octahedrites are the most common ones. And it refers there to Widmanstätten figures, and I'll show you in a minute what those are. Ataxites, which are pretty rare, and hexahedrites, which are also quite rare. We have two of these in the display here. We have several octahedrites, including the biggest ones that are on the bottom of the case. And we have one hexahedrite. Now, Widmanstätten figures are these very distinctive patterns of intergrown crystals that show up. In order to see these, you have to slice the meteorite, and then you have to etch it with acid. And that makes the surface reveal these patterns. And there are several meteorites in the case here that have been sliced and etched, so you can see the Widmanstätten figures. Those are like fingerprints. If you have hundreds of fragments from the same meteorite, they're all going to show the same pattern. But if you have two meteorites showing Widmanstätten figures, and they're two different meteorites, the pattern will be different, just like fingerprints. So hexahedrites, the middle one, ataxites, do not have any figures inside them at all. They're boring. But the hexahedrites will, if they're etched, show something called Naumann lines. Naumann or Newman, depends on what language you're in. These are straight lines. They look like cut lines on a piece of wood. And in that specimen there, they're going this way. If you can see them, they're very faint. And that's a cool specimen because that big wedge-shaped thing there in the middle is a mineral called troilite. It's an inclusion in that particular meteorite. Troilite is one of the forms of iron sulfide that you find in meteorites. Now that was iron meteorites. The intermediary, these are very rare, but they're very cool. These are the stony-iron meteorites. They have characteristics of both iron and stonies. They are a mixture of pure iron and silicate minerals, many of which are the same minerals you find on Earth. And there are only two kinds of these: mesositerites, which have a bigger variety generally of the silicate minerals in smaller pieces, and pallasites, which are the most spectacular of meteorites, and there's two of them in that right-hand case. Those greenish crystals that you see there are the mineral olivine, which is an iron and magnesium silicate mineral that you find in lots of terrestrial rocks. And these are pretty rare, and they're very popular because they can be really pretty when they're sliced like this. Now, chondrites, or stony meteorites, are the most common kind of meteorite, but they're also the hardest to find. They do not attract a magnet most of the time, They look like just a plain old rock. You look at that one in the middle there, if you saw that in a stream bed or something, you'd walk right by it, because it doesn't look like anything. Most meteorites are discovered in places where if there's a dark rock, it stands out. So places like a cornfield, or a desert, or Antarctica, where there generally are no rocks sticking out. If you're walking through a snowfield or something and you see a dark rock, then, you know, your brain should say, hey, that might be a meteorite. But if you're walking through, say, Lassen Park, where all the rocks are black, it's probably not going to be something you're going to find. So when we talk about chondrites, one of the cool things is chondrules. Now, chondrules are round, or actually they're spheres, of silicate minerals, and they are the first things to form. When these things are first forming billions of years ago, out in the primitive solar system as it was just coming together. So those chondrules in these meteorites are believed to be some of the oldest solids in the solar system, like 4.6 billion years old. So in the picture in the lower left, the chondrules are quite large. Some of them, they're up to about 1 inch. The one in the middle, those are typical. You know, there's lots of little tinies you can't see, and a few larger ones that are like 1/4 inch. That picture on the right-hand side, one way that geologists look at rocks and try to tell the relationships among the grains, there are lots of things you can learn from this. You make a very thin slice of it with a saw, and then you grind it down until it's only 30 microns thick, so you can see light through it. You can do this pretty much with any rock. And then you look at it in a special microscope that has polarized light. And you get all those gorgeous colors, and those colors can tell me what minerals those are by the colors and how the thing behaves when I change the kind of light that goes through the microscope. So the chondrules show up really nicely in a cross-polarized picture like that. So chondrites, again, like irons, come in 3 different kinds. There are ordinary ones, which are just plain old, and then there's carbonaceous chondrites and achondrites. Ordinary chondrites, of course, they're ordinary. They are the most common kind, and they look like those 2 pictures in the bottom there. The surface tends to be dull and dark because they often develop what's called a fusion crust. As they come through the atmosphere, the outside of them gets a little bit baked and possibly melts a bit, and so it turns to glass. And so it gives you that nice smooth but very dark surface, and you have to break them or cut them to find that lighter colored, more granular interior. So all meteorites within these general categories are categorized over and over again, more and more detailed, by people who are they're looking at them under a microscope for texture differences, how much iron do they have in them, and what are in the case of chondrites, what do the chondrules look like and what's in them. So achondrites, and I only have 1 achondrite in the cases here. It's a eucrite. It's that first odd kind. And these are things that they believe come from asteroids that are slightly differentiated. What this means is that the asteroid is big enough and old enough that it has developed some layering. It's not all just a big blob of the same stuff. It's possibly got a core, like the Earth has 3 layers, because the Earth is a differentiated planet. It has, over time, different compounds have become concentrated in different layers within the Earth. That happens on asteroids sometimes too. So eucrites come from one of those asteroids, mostly from an asteroid called Vesta, which is a large one. And Vesta, I think, is somewhere floating around in our solar system. Also, you hear about lunar meteorites and Mars meteorites. Those are pieces of those bodies that have been flung out into the solar system by impacts. So if an asteroid hits the moon, pieces of the moon are flung out into space. And they float around as meteoroids, and some of them land on Earth. That's where lunar meteorites come from. And the same thing with Mars meteorites. Carbonaceous chondrites, and I think I have one or two in the cases. These are very special types of chondrites. Because they contain some organic molecules. In some cases, amino acids. Amino acids are the building blocks for proteins and lots of other basic life forms. And there are people who believe that these types of meteorites brought the first carbon compounds to Earth and were the origin of life on Earth. So I don't know enough about that to comment on it one way or the other, but there is a very large piece of the Murchison carbonaceous chondrite in one of the cases. It's about the size of a softball, and that comes from a place in Australia. Okay, when you're talking about meteorites, one of the things that you mention is whether it was a fall or a find. If somebody just walks along and finds a meteorite, then you record the date that you found it, you record where you found it. But if you see it coming down, and then you run out and find it, that's called a fall, because you saw it fall. So most meteorites are finds, because actually seeing one come down and then being able to go find it is pretty unusual. But it does happen. There was one in Canada a couple of years ago where the thing shattered and it hit. So the owners of the different fields that it landed in went out and sort of mined their cornfields for it. And if you're walking along somewhere and you find a meteorite, it doesn't automatically belong to you. It belongs to whoever owns the land it's on. So if you find you're in a state park and you find a meteorite, it doesn't belong to you. It belongs to the state of California. And it doesn't really count as a meteorite unless you can document it. So it doesn't do you any good to stick it in your pocket and make off with it, because you can't prove that it's a meteorite without showing people where it came from. And in order to verify that something is a meteorite, you have to get someone who works on meteorites to agree to do the analysis of it. But if you're in an area like Canyon Diablo in Arizona, that is a huge meteorite that broke into lots and lots of pieces when it hit the ground, I think about 50,000 years ago. And so you can still walk out there and pick up pieces of it. And that place is owned privately. So I think they probably will, for a fee, let you wander around and see if you can't find some. Meteorites, each one has a name, a unique name, usually for some geographic feature that was near where it landed. So in the case of Canyon Diablo, which is probably the most common meteorite for sale these days, Canyon Diablo is a little tiny town. It's a ghost town now. But back in the late 1800s, they say it was a worse town than Tombstone. That, had lots of yelling and drinking and shooting and things. But right now it's just some old foundations and stuff left. But it's the closest town to Meteor Crater where that meteorite landed, so they gave it that name. Now when a meteorite hits the ground, if it comes straight down, it makes a circular impact site. The mark that a meteorite makes on the ground is called an astrogleam. Not a word you hear very often. Most people just call them craters. And the ones that are still visible on the Earth's surface are usually in deserts. Because if that's the meteor crater there in Arizona on the left, and it still looks pretty fresh, but they hardly get any rainfall there, nothing grows there. So other than people walking over the rim, there's really no erosion. Nothing going on there that would break down that earth form.
How old would it be?
About 50,000 years. And that's about a mile wide, that hole. And there's meteorite bits scattered in the desert all around it. The picture on the right, that's a crater on Mars. And you can imagine the meteorite coming in and sort of skidding to a stop at an angle. Those are more unusual because they're probably not more unusual, they're just harder to spot. So there are probably thousands of meteorite impact sites on Earth that people haven't found yet because they're eroded, or they're buried under a jungle, or they're under the ocean. There are lots of places where they can be hidden. Since they started taking satellite photographs, a lot of them have been found because they show up better from way up in the air. Sometimes meteorites will explode before they hit the ground. And the most famous one of these is the Tunguska explosion that happened in 1908 in Russia. The picture on the right is an artist thinking this is what it looked like. It was a huge aerial explosion, and the thing was totally destroyed. There are no bits of meteorite on the ground around this thing, but the force of the blast, apparently they could hear it in England. It was so loud. And it knocked down huge forests of trees for many miles in all directions. And for many years they couldn't figure out why those trees were all dead and why they were all laying down, and they're, spread out. They're not all in one direction. They're spread out away from where the blast was. So a lot of people wanted that to be Martians.
What caused the blast?
The disintegration of the meteorite due to the friction of its travel. It just wasn't strong enough to stand, to last long enough to get down to the
And
ground.
all of a sudden,
It just kaboom. It doesn't happen very often, but when it does, it's pretty devastating and pretty distinctive. Back in 1987, some people who were looking for caves to dive in the Yucatan, discovered what they thought was part of a large meteorite impact crater. So as more and more study was done of that, right about the same time, two men named Alvarez, Walter and Luis, who are physicists, their father and son, working at UC Berkeley, were coming up with this theory that huge meteorite impacts can cause so much disruption of the atmosphere. They can put so much dirt and dust in the atmosphere and change the chemistry of the air to the point where they change life on Earth.
mm-hmm.
So when they published that back in the 80s, right about the same time people were looking for more impact structures, people found this really huge one that back at the end of the Cretaceous, about 65 million years ago, when this happened, that point on the Yucatan Peninsula was totally out in the ocean. And so whatever this thing was, it hit the ocean and was still going fast enough when it hit the bottom of the ocean to make a huge crater and to send an incredible amount of stuff up into the atmosphere. And it had been known before that that there was a massive extinction at the end of the Cretaceous. 65 million years ago, about 75% of the terrestrial species on Earth died. And nobody really knew why. And so this is because this theory has become more accepted, and people are now looking for other impacts that might have affected, maybe not globally, but locally, the evolution and extinction of various groups of animals and plants. So this is an instance where science is not static. Things are always changing, and sometimes it's not really high-tech science. It's just you happen to find something that sets off somebody else saying, hey, I bet that relate to this, and you come up with a new theory. And of course the satellite images helped a lot, but it still would have happened without that. The satellite images are helping people find impacts and meteorite fields that are in like the Central American jungle and deserts where nobody ever goes, and the polar ice caps as well. Now the minerals that make up meteorites, most of them are very simple compounds, or they're just what we call native elements. They're single elements, including things like diamonds. Most of the diamonds that come in meteorites are called nanodiamonds, meaning they are so small that you can't see them with the naked eye, but they're in there. And things like cohenite and haxanite, there on the left, those are stable where there is no gravity. And as soon as you put them into a situation where there's gravity and water, they become unstable and they chemically change naturally into other things. In those cases, they turn into a mixture of graphite and taenite. Kamacite and taenite are the two minerals that make up most of the iron meteorites. They are natural minerals that are made mostly of iron with some nickel in them. Yeah.
How are they able to come up with the formulas for the cohenite and haxanite?
You get a nice fresh one. And some of these things still exist on the inside of meteorites that haven't been cut or exposed to the air. So, and there are some minerals that only are found in meteorites. And they're shown, there's a few of them shown in purple here. Now I only showed the most common ones. There are about 350 different minerals that are found in various meteorites around the world. And there are people who do nothing but study the different kinds of minerals that you find in meteorites and in lunar rocks. And they're all hoping for Mars rocks soon.
If those two over there, cohenite and haxanite, are unstable on the Earth, should they also be in purple, or are they found in minute amounts?
No, they're found
as well?
in meteorites that have not had time to alter yet, and also on the inside of large meteorites.
Yes, but are they found on the Earth?
Yes.
Ah.
Oh, no, they're not. A number of these things are found, you're right, they should be purple. Some things like kamacite, 99% of the time it's in a meteorite, but not always. Now, tektites are something that you see a lot of mineral dealers sell them. People use them for jewelry, and they're all over the place. But they only are found in a couple of places on Earth. That map shows you where the large fields of tektites are found. Not all meteorite impacts make tektites. It has to be a fairly large meteorite, and you have to have the right conditions. Also, tektites are glass. They're what we call impact glass. If you hit something hard enough, it will liquefy. The force that you impose on that solid will cause it to become a liquid. And if this is a meteorite doing that, these blobs of liquid, which form from the rock that was already here, or the soil get flung up into the air. And while they're in the air, they harden. But because they're traveling so fast, and this happens really, really quickly, whatever elements are in that soil or that rock are in that liquid, but they don't have time to form minerals before they harden. And that's what glass is. Glass is anything, any combination of elements that are random in a solid.
Like obsidian.
Obsidian is another form of natural glass. And that's lava that comes out so quickly that the elements in it don't have time to organize themselves into minerals. And they just sort of freeze. If you took a piece of obsidian and melted it and cooled it off slowly, you'd get a rock. You wouldn't get more obsidian. So to make glass, you have to cool it off really fast. And most of the meteorite, or the tektites that you see out there in collections and for sale are from that big red area in Indochina. It includes Thailand and the Philippines and parts of New Guinea and Indonesia. Nobody really knows where the impact was that produced these. And the same thing goes for the ones from southern Australia. Nobody's really sure why they're there. Libyan desert glass is really pretty sometimes. It tends to be a lighter color. And the green one there in the lower left, that's what's called a Moldavite because it comes from the Moldavian region in the Czech Republic. And that's the stuff that's most commonly used for jewelry. I've even seen it on the Jewelry Channel on cable. I don't think those people know that it's just glass. But if it's cut, it's a beautiful green color. It's really nifty. But it is not from outer space. It is not a meteorite or anything from out there. It is a terrestrial material that was affected by a meteorite, but didn't actually come from there. And one of the other things about glass is that it doesn't last very long on the ground surface. If you've ever been up around Clear Lake, where there's a lot of obsidian around Mount Konocti, never pull off the road up there because there's obsidian everywhere and you can't see it. If it's been out in the rain and the wind for even a couple of years, it develops just a worn sort of look to it. It just becomes another gray rock. And you have to break it open to see the shiny, dark, glassy stuff on the inside. So, particularly if tektites are really small, after a few years, particularly if they're in some jungly place, they're going to be gone. They will break down chemically because they have no crystalline structure to give them any kind of physical strength.
And volcanoes also produce tektites?
No. The only thing that produces a tektite is impact. So there are three kinds of natural glass. Tektites, obsidian, which is volcanic, and a thing called fulgurites. Fulgurites are where a source of energy hits the ground, usually lightning. And it melts wherever it hits, and that energy travels down into the ground and forms what looks like an upside down tree. So the biggest part of it will be right at the point where the lightning struck the ground, and then it sort of dissipates into the ground, melting as it goes. So you can get an upside down glass tree in the ground. It's really nifty. We have one at the museum that was caused by a PG&E line that hit the ground. And it's not pretty, it's just a big blob. But technically it's still glass.
Does voltage matter?
Well, the more voltage, the more energy, so the more stuff will melt.
But is there like a certain amount?
I don't know. Now these are the meteorites that are on display here. These are from the Academy's collection. If you have meteorites, or you want to start your own collection, the main thing you want to do is, one, make sure that the information that comes with it stays with it. And you can do this by keeping the labels that come with it, or whatever paperwork there is. Make your own labels, or put a number on it, or some kind of a mark so that you can tell that that is what you have. And that's a really good idea with meteorites, particularly because they all kind of look the same. And so the Academy ones all have numbers on them. And those numbers are in the second column there. That's what tells me, and I can look it up in the computer or the handwritten catalog, and it will tell me who gave it to us, how big is it, when did we get it, and then the information on the right-hand side, that's the information that's available for that particular meteorite. So if you go out and you get a piece of the Vaca Muerta, it will always be a mesosiderite that was found, part of the one that was found in 1861 in the Atacama Desert in Chile. So I tried, when we put this exhibit together, we tried to come up with as many different kinds as we could that wouldn't make the case collapse. The Oroville, which is there in the lower right-hand side of the right case, weighs about 43 pounds. It's very dense. And that's an iron meteorite from Oroville up in Butte County. And it's I paid somebody years ago to have it sliced because it was just a single individual. Nobody's ever found any other meteorites around there. So that probably just landed all by itself. It didn't break when it hit the ground. So that's a very rare meteorite. There aren't that many meteorites from California, or that have been found here so far. So, and that one is even more interesting because the Academy acquired that right after it was found. Back in the late 1800s, and the Academy of Sciences was on Market Street in 1906, and we burned down. And so the building burned around it. And so after the fire and the earthquake and everything, when they were cleaning up, they went in and went through the ashes and pulled out what they could, and nothing happened to that.
It's a rock.
It's a rock. So, that's all I've got for you today. I will stick around and answer questions, and I encourage everybody who's here today to come up and take a look at the actual meteorites. And if you want to learn more, there are some excellent books out there, and there are lots of websites. Sort of beware the websites, because a lot of them were put together by dealers. So if you're going to go to dealer websites, don't just go to one. You know, learn from various places. Like all things on the internet, don't rely on just one site, because you don't know who's out there writing this stuff. But if you get a book, the book is probably right, because books go through editors and peer review, and they're a lot more likely to be accurate. So thank you for your kind attention.
Thank you.